right, how's everyone feeling today?
Totally awesome, sir!
All right, lesson 19, question. How can motion graphs be used to solve problems? There's two key features on a velocity time graph that can be extremely useful when you're solving motion graphs. I want to tell you about those two key features, and then I want to show you examples. Okay? Everyone have the question copied down? Good to go? All right. Let's say we have a velocity time graph, and let's start off with a nice simple one. One where the velocity is constant. Let's say it's constantly positive 20 meters per second. And the object moves forward for 3 seconds. These facts that I'm about to give you are true for all velocity time graphs. I'm just using a very, very simple warm-up example to show you how this works. Fact number 1. The slope of the graph, when it's a velocity time graph, always represents the acceleration of the motion. So for this example, if I looked at the first 3 seconds and I calculated the slope of that line, we know that slope is equal to delta y over delta x. Well, the y value doesn't change. It's constantly positive 20. So if I wrote like y2 minus y1, it would be positive 20 minus positive 20. The change in y is 0 meters per second. Velocity didn't change, and the change in x would be the 3 seconds. And notice 0 divided by 3 is just going to be 0, but even the units come out. Meters per second, those are acceleration units. And if written properly, that's meters per second squared. So notice the slope is 0 meters per second squared. What's the acceleration? 0 meters per second squared. Fact number 1 verified in this simple case. Fact number 2 has to do with the area under the curve. Now it's kind of weird because this graph is a straight line. And even though it's a straight line, in general, the graph is referred to as the curve. So this here is the curve. If you find the area underneath this curve, the area underneath the graph, it ends up telling you the change in position or the displacement. So fact number 2, the area under fancy way of saying under the graph, represents the total displacement. So if I wanted to find the area under the curve for the first 3 seconds, here's my curve. I drop lines down at 0 and at 3 seconds. The last boundary is the x-axis itself. The x-axis is the other boundary right here. So if I wanted to find the area under the curve from 0 to 3 seconds, it would be this area right in here. Now when we go to calculate that area, we see in this case, it's a rectangle. So area equals base times height. But in this case, the base is 3 seconds. This is the base right here. 3 seconds. The height is this right here, which is the same over here. So what is that height with units? Positive 20 meters per second. And now if we multiply this out with units, 3 times 20 is 60, but seconds times meters per second, the seconds cancel out, and you're left with meters, and voila, that tells you the total distance traveled.
Total displacement.
The total displacement, exactly. Thank you. Which makes sense, because if you're going 20 meters per second, hey, I'm going 20 meters per second, how far would you travel in 3 seconds? 60 meters. So these two facts right here are very, very useful when solving motion problems. When you go to do lesson 19 homework, on the syllabus it specifically says to draw velocity time graphs. So now you have to include that in your proper problem format. Now, I want to apply these two facts to one more example. Question?
Yeah. Let's say like the curve is all like funky looking.
Yes.
How would we find the area under the curve? Wouldn't we have to like use calculus?
Correct. Correct. So here we're only going to be finding the area underneath the curve when it's a straight line. But you're absolutely right. If it wasn't a straight line, if it was a funky curve, that's where calculus comes in. And finding the area underneath the curve in calculus is called integration. Finding the integral. Fancy dancy way of saying finding the area underneath the curve. Okay, so let's go to a sample problem.
Should we write this?
You should take a moment and yeah, actually, you're probably best off actually copying this down here. What we have is a ball being thrown upward. We're going to analyze the ball once it's no longer in contact with my hands. Once I throw the ball and it's no longer touching my hands, that's time 0. And at time 0, we're saying that the ball is going to be going upward, positive 30 meters per second. Now, you know how we've been doing all these problems left and right? Well, we have to now look at a vertical reference frame. Our horizontal reference frame, if something was going to the right, we said it was a positive velocity. And if something was going to the left, it was a negative velocity. We had to establish that before we did all of our problems. Well, now we're going to establish a vertical reference frame. And if something has an upward velocity, positive. But if something's moving downward, negative velocity. So we're going to analyze this ball the moment it leaves my hands, right to the moment, right before it hits my hands, while the ball is airborne. The whole time it's not touching my hands. So the ball starts at A, goes up to B, comes back down to C.